Good evening. We are proposing a BCI device that grants some personal control over the environment. Meet Mindful, our solution to unlocking the environment with your mind. Our device will utilize a graphical user interface of various actions that control an individual's environment utilizing a variety of EEG signals. Benefits of this device include reduction of care time, scalability, and simplicity. Mindful's GUI provides a myriad of patient and healthcare provider-driven features. Patient features include the decision array and a yes-no option arrow, while healthcare provider features include a vitals monitoring display and manual options such as sleep, shutdown, restart. Mindful's main feature revolves around the decision array. As simple as it sounds, the decision array is an array of actions that can be chosen. The two main benefits include simplicity, which is proven by existing literature, while scalability and adaptability revolve around the ability to increase the number of actions and also add different actions. It works by eliciting EEG signals to control action selection. Actions then glow green when selected, and then the user confirms if the action is desired. Otherwise, it will return home. Yes/no options will be explained later.
The user interacts with the decision array using a cursor or highlighted square. The cursor is controlled using mu rhythms, specifically imagined right or left-hand movement. Imagined right-hand movement moves the cursor 45 degrees clockwise, while imagined left-hand movement moves the cursor counterclockwise. Once the user has moved the cursor to the ideal location, the user can select a tile by eliciting a beta rhythm through intense concentration. If the user would like to cancel the action or return the cursor to the home position, they can use a blink pattern to elicit an alpha rhythm. Lack of action will cause the screen to dim over time and gradually enter an inactive state. User input will wake this screen from this inactive state and return the screen to full brightness. Upon the detection of REM sleep, the device will enter a disabled state where it will not respond to user commands. This is to prevent accidental actions in deep sleep. This will be detected using an algorithm for detecting REM sleep by Inbaz and Rodriguez-Villegas. We have specifically chosen signals with frequency characteristics that are easily identifiable. They are both easy to detect while easily controlled by the user. While many of these electrodes do share the same frequency band, each signal is collected by a unique set of electrodes on different lobes of the brain to ensure that there is no interference between collected signals.
The patient wears an electrode cap in order to record changes in EEG. To detect mu rhythms, electrodes lie on the motor homunculus to record the imagined motor movements. Electrodes positioned over frontal parietal attention network nodes record the increased amplitude of beta rhythms with increased user attention. Electrodes placed on the occipital lobe, the visual processing part of the brain, records alpha rhythms. To discern whether the user is asleep, the occipital and frontal lobe electrodes record sleep cycle activity.
On screen is the main block diagram for the system. If the patient is not awake, the device will stay disabled and not allow for further action. If the patient is awake and imagining motor movement, the cursor will move in the desired direction. If this is the desired action, an increase in mental focus will select the action. If it is not, the imagining of the motor movement can be continued to move the cursor further. If the patient decides that no action is desired, the eye blink pattern will reset the cursor to the home tile. Next, we have the action subdiagrams. After initial selection, the actions will execute to the extent desired by the user, returning the cursor to the home tile when finished. For the body up action, an extended increase in beta rhythm will increase the back angle of the bed, with the angle not surpassing an upper limit determined via the resistance force. The body down action will decrease the back angle of the bed upon the extended beta rhythm increase. In a similar fashion, the front angle of the bed can be increased or decreased via two separate functions. The yes-no action will bring the user to the separate yes-no matrix on the right-hand side of the tablet. The user can then highlight their desired yes or no response by moving the cursor with mu rhythms. To exit the matrix, the eye blink pattern is used.
It can be turned on or off with increased mental focus based on the initial state of the light. After medical assistance is requested, the user will be asked to confirm or cancel their request. If no selection is made after 5 seconds, assistance will be called. To prevent user injury, there will be a limit to the angle that the user can adjust their bed. The patient will not be able to raise their bed more than 45 degrees from the ground. In addition, the BCI will stop the bed movement after a certain resistance force threshold is met. To prevent eye strain, the screen will go to sleep after 10 minutes of inactivity. To prevent accidental or unintentional selection, the BCI will ask the user for confirmation or cancellation when making a decision. When calling for emergency medical assistance, the user will be prompted with a dialog box after selecting this option. The user has 5 seconds to confirm or cancel their request. Failure to make a decision during this time will be taken as a confirmation and emergency assistance will be contacted. The user will be able to cancel their request any time after assistance has been contacted.
Our device is feasible because our rhythm-action associations, ease of use, and training are proven in literature. Also, our programming prevents unwanted actions. Mindful will help quadriplegics achieve more freedom through its simple-to-use, adaptable, scalable, and customizable interface.